One of the more helpful techniques that we're going to talk about in this video comes into play when we're looking at differentiating much more complex formulae, and this is called logarithmic differentiation. Now this helps us by removing a layer of complexity within the equation and within the function itself, such that we're able to differentiate with respect to a logarithmic version of each side of the equation, because we all know how to do derivatives of logarithms, so bringing that into play is something which actually can be beneficial. Now, there's a couple of things we do need to remember for this. First thing is that when we want to use this, we need to somehow bring it down and simplify the equation to make it easier, so we have to take logarithms of both sides. That's the key fundamental characteristic of logarithmic differentiation. But in order to do that as well, we have to remember the rules of logarithms. Now, these are a reminder of the three key rules of logarithms that we've covered at National 5 and higher level prior to this. So the first is that the logarithm of x times y can be split into the logarithm of x times the logarithm of y. ln of x divided by y can be split into ln x take away ln y, and ln x to the power of r, we can bring the power down and make it r times ln x. We need to remember and use all three of these at various points when we're taking logarithms of both sides. This will help us manipulate things and actually turn quite a complex function into something much easier to work with. So I'm going to show you a few examples of what I mean to demonstrate it to you. First one, let's imagine I want to differentiate y equals 2 to the power of x plus 3. Now instantly, you'd normally look at that and think, excellent, that's quite a nice straightforward easy one to differentiate. I should be able to do it. The issue is that the power is an x plus 3. So the power is the dependent upon x part of the equation. So in order to do this and make it a heck of a lot easier for ourselves, if we take logarithms of both sides and then use the rules of logarithms, we can then turn it into a chain rule function which we're able to differentiate from there. So what we'll do is let's start by taking the logs of both sides, so natural logarithm of both sides. So I've got ln y equals ln of 2 to the power of x plus 3. Now this on the right hand side, ln of 2 to the power of x plus 3, what I can do is I can take that and rewrite it as x plus 3 times ln 2. Now I can use the third rule we discussed previously in order to manipulate it and do it like this. Now, what to notice then is ln y, that's a function dependent on x, but now what I've done is taken something which has x as a power of the part of the function, to bringing it down and turning it into an ln of a constant times this. So essentially ln of 2 is just a more complex constant if we were to calculate it out. So I've actually made it a heck of a lot easier for myself by doing this. Then I could take derivatives of both sides and then simplify it through and work it out. So if I've got ln y, derivative of that is 1 over y times dy by dx. Now the reason that we say it like that is, remember, we're saying y is some function with a dependence upon x, so that's why, as well as the 1 over y, we have to do times dy by dx. Now this side here, what we're able to do is, if you want to think about it, we could essentially have that as ln 2 times x plus 3 times ln 2 if we were to manipulate the bracket and multiply it out. So if we were to do that, what would happen is when we take the derivative of that, what we would end up with is quite simply ln 2. What I can then do is shift the y across here, so I end up with dy by dx equals ln 2 times the y, and what I can now do is substitute back in for my y, and I can get the equation completely in terms of x. So if I substitute back in, I get dy by dx equals ln of 2 times 2 to the power of x plus 3. So there you go, I've taken the derivative of it, and it was that first key initial step of taking logarithms of both sides that actually reduced the complexity and allowed me to do it as quickly, easily and as efficiently as I have done there. Second one I'm going to show you is find dy by dx when y equals x to the power of x. Now again, this is one that initially you might look at and think looks straightforward and easy, but the fact that the base and the power both have a dependence upon the same variable adds the extra level of complexity. So taking the logarithms to both sides will allow me to split that up and make it a much more straightforward function to work with. So if I do that, I'll have ln y on the left equals ln of x to the power of x. Now I can rewrite this side and make it x times ln of x using the rules of logarithms that we've discussed before. What I can now do is take the derivative of both sides with respect to x, then manipulate it about and see if I can simplify it in the way I want. So ln of y, derivative of that, is 1 over y times dy by dx. And the right hand side, remember, focus on this version of it here for the derivative. Well, that's something dependent on x times something dependent on x, so we have to use the product rule. So for that, I'll end up with ln x plus x times the derivative of ln x, which is 1 over x. So simplifying that, what I'll end up with is ln x plus 1. So I've got 1 over y dy by dx is equal to that. So what I can then do is multiply through by y, and I get dy by dx equals ln x plus 1 in a bracket times y, and I'll substitute back in for y, and I get dy by dx equals ln x plus 1 times x to the power of x. So there you go, I've calculated my derivative like that. So again, I've used the rules of logarithms plus the rules of my differentiation, so my product rule, in order to be able to calculate it. We can bring everything together, everything that we've looked at and everything we've worked on, to answer questions along these lines, and even ones with an extra step in complexity. Like this bad boy. So find dy by dx when y equals 2x plus 1 to the half times 3x minus 1 to the 2/3 all over 4x plus 3 to the 3 over 4. Now that's the kind of equation you might initially look at and think, geez Louise, that's going to be a fun one to do. Now you could do it using a combination of product rule, quotient rule and chain rule. However, it actually becomes a lot easier when we use logarithmic differentiation. Because if I take the logarithms of both sides, I have ln y equals ln of everything that's here on the right hand side. So 2x plus 1 to the half times 3x minus 1 to the 2/3 all over 4x plus 3 to the 3 over 4, like that. Now you're looking at it going, how has that made it easier? Well, what I can do is use the rules of logarithms to split this bit up here on the right hand side. Because what I can do is make that ln of 2x plus 1 to the half plus ln of 3x minus 1 to the 2/3 take away ln of 4x plus 3 to the 3 over 4. Now again, this still isn't something that looks exactly too appealing to us. However, we can then use another rule of logarithms to bring the powers down to in front of each of these. So I'd end up with a half times ln of 2x plus 1 plus 2/3 times ln of 3x minus 1 take away 3/4 times ln of 4x plus 3. So that actually will make it a lot easier for us to find the derivatives. So what I now do is take the derivative of both sides and see what I can get from that. So derivative of the left hand side will give me 1 over y dy by dx. And if I look at the right side and I do derivatives of each term individually, first term will give me a half times 1 over 2x plus 1 times that by 2. Then I have plus 2/3 times 1 over 3x minus 1 times 3, again using the chain rule within each of these. And then my final term would be minus 3 over 4 times 1 over 4x plus 3 times 4. So if I go through each of these and simplify it now, what I'll discover is a half times the 2 there, they cancel. I've got my times 3 and my divide 3 there, they'll cancel, and I've got my divide by 4 times by 4 there, they'll cancel as well. So what I'll end up getting for this is I'll get 1 over 2x plus 1 plus 2 over 3x minus 1, take away 3 over 4x plus 3. Now the next step would be to start simplifying it. Well, in order to do that, what I could first do is take everything here and stick it all over a common denominator and simplify that down. If I were to do that, what I'd end up getting is 1 over y dy by dx equals 2 bracket 5x squared plus 11x plus 3, and then on the denominator I'd end up getting 2x plus 1, 3x minus 1, 4x plus 3. So that's what it would be at that stage. I've then got to get rid of the 1 over y. So what I'll do is I'll take the y across here, multiply it, but then I'll substitute in what I know for y here. So this original fun looking equation right there. Once I've done that, we simplify it, manipulate it enough so that we can get rid of any powers or brackets and cancel things out that we need. And if I were to do that, I'd end up with a final answer for dy by dx, which would be given by 2 bracket 5x squared plus 11x plus 3 on the top, and I'd have a denominator for that fraction of 2x plus 1 to the half, 3x minus 1 to a third, and then 4x plus 3 to the 7 over 4. So again, another fun looking equation that we've got to work with there. Now that, it may not seem it, that has taken a level of complexity away from it from us so that we're able to work a little bit easier with it and actually work it through in fewer steps than any other method that we've got. It can seem like it's adding to the complexity sometime. So initially you might have looked at it and thought, geez, this isn't exactly making it look easier. But once we've used our rules of logarithms, especially when we got to a stage like this, what we actually have ended up with is just something, a constant, times the logarithm of a function. And we know that log of a function, to take the derivative, we do 1 over the function times the derivative of that function. That's a lot quicker and easier to work with than working with product rules involving brackets with fractions, numbers inside, and quotients where we also have fractional powers and numbers within it. So it just makes it a little bit easier in the long term despite an initial anticipation where we think, oh, this might not be very good at all. It does work and it is good to know.